Hello everyone and welcome to lecture 2 in this course, an introduction to inorganic chemistry. Now we've spoken about how electrons fill atomic orbitals in a very basic sense. We've spoken briefly about the Aufbau principle in lecture 1, and we briefly discussed the order in which electrons fill atomic orbitals. We then moved our discussion on to talk about how electrons are shared between atoms in molecules and ions. We looked at Lewis structures and we said that they're great ways of looking at atomic connectivity, the arrangement of atoms in terms of links between atoms in a molecule. But we said that the problem with Lewis structures is that they don't necessarily tell us anything about molecular shape. We then moved on to VSEPR theory, and we needed our Lewis structures to be able to conduct or implement the VSEPR model. And we looked at ways of, fail-safe ways of predicting molecular shape based on an arrangement of electron density. And we spoke also about the importance of the difference between regions of electron density. So there are a number of regions of electron density around an atom, and they may be lone pairs, or they may be shared electrons through a bond. What I would like to speak about today is a topic that will increase the scale of complexity about how we look at the sharing of electrons between atoms in molecules and ions. So I hope that by the end of this session you will have an understanding of how atomic orbitals can be combined to give molecular orbitals, and an understanding of how electrons fill these systems. This is a very brief introduction to something called molecular orbital theory. And I'm not going to examine this. Okay, so this will not appear on the coursework, or it will not appear on the end of year examination. But what I want you to have is a qualitative understanding of how atomic orbitals overlap between atoms to form a chemical bond and form something that we call molecular orbitals. And then I'd like you to have a qualitative understanding of how electrons fill these systems. So molecular orbital theory in its essence is a sophisticated model of bonding. And we can apply it to very simple molecules. So we can apply it to the kinds of molecules we've been looking at, basic, very simple, often diatomic molecules such as hydrochloric acid or perhaps hydrofluoric acid. But we can apply this to much more complex systems and gain understandings about energy levels within those systems. What we do is we take the theory of atomic orbitals, and you'll get this in other modules. So the chemists will learn about atomic orbitals and wave functions and that kind of thing in the physical chemistry module of this course. But needless to say, we have theories of atomic orbitals. And what we do is we generalize those to molecular orbitals to describe energy levels within a molecule. And all that happens is that to make a molecular orbital, atomic orbitals overlap and share space. So in the simplest form, two atomic orbitals on two atoms will overlap to form molecular orbitals. What we're saying then is that electrons, from a mathematical perspective, spread over all atoms in that molecule and bind them together. And in molecular orbital theory, this is essentially a very basic description of a chemical bond. Now, as with any other theory, we have to make some assumptions, and we make up an orbital approximation. We assume that the wave function, the mathematical parameters that describe the electron in an atom, adequately describe the electrons in the molecule. So we assume that all of the mathematical theory that we apply to the atom also applies to the molecule when combined or when made up of several of those atoms. And those wave functions that we use to describe the atomic orbitals on the atom are then used to make these molecular orbitals of a molecule. And the square of that wave function gives the probability distribution of an electron in a molecule. Now, the question is, when making these approximations, is we have to think about what is the nature of a chemical bond, what happens when two atoms share electrons to form a bond, and a reasonable approach is to describe that bond by the superimposition of atomic orbitals that are contributed by each atom. So let's think of a very, very simple diatomic molecule, something like hydrochloric acid. There is a hydrogen atom and a chlorine atom, and they share electrons to form a bond. So it must be that somewhere atomic orbitals which contain electrons on each of those atoms, the hydrogen and the chlorine, approach, overlap, and form some kind of new orbital, a molecular orbital, through the sharing or the overlap of those atomic orbitals. And we call this the linear combination of atomic orbitals. And that linear combination is a sum, and it can have various weighting coefficients. We'll speak about that in a moment. So we have to first describe what we call the basis set. What atomic orbitals are going to overlap on two atoms, if we're talking about a very simple diatomic molecule, to form these molecular orbitals or these chemical bonds? Well, it would make sense to use the valence shell atomic orbitals on the respective atoms. And we use the valence shell because these are the ones farthest away from the nucleus on the exterior of the atom and are able to overlap. And we can describe those as a wave function, but I want you to think about this qualitatively. I don't want us to worry about the mathematics here. I just want us to think about what is overlapping and what is being formed as a result of that overlap. But you'll see there that you can describe the molecular orbitals, in this case for hydrogen, molecular hydrogen, as the overlap of two hydrogen 1s orbitals. So all we're saying in this theory is that two hydrogen atoms come together and their valence orbitals, their valence atomic orbitals, overlap to share electrons. And when those atomic orbitals overlap, mathematically, we describe them as a molecular orbital. And you'll see in the equation at the bottom there is essentially just a mathematical description of this process. So there is a Ca and a Cb, and these are coefficients in linear combination. These show the extent of the contribution from each atomic orbital to the overall molecular orbital. Now, it just so happens that in molecular hydrogen, that is equal. Both of those 1s orbitals overlap in an equal manner. And then you see the Xa term, and these are the actual atomic orbitals that are being combined. So in the case of hydrogen, it's the hydrogen 1s atomic orbital from atom A, or hydrogen A, and the hydrogen 1s orbital from atom B, or hydrogen B. Now, it's important to remember that both atomic orbitals, again, I'll leave the discussion for now at quite simple diatomic molecules. Both the atomic orbitals that are overlapping contribute to the final molecular orbital. And if they both contribute, then we gain some kind of interference between them. And that interference can be constructive or destructive. Remember, these are wave functions, so they have amplitude. Now, when two orbitals overlap then, and they interfere, this interference creates bonding and anti-bonding molecular orbitals. So a really important point here is that in this model, and there are multiple models of bonds, but in molecular orbital theory, we are describing a chemical bond as two atomic orbitals overlapping. When those two atomic orbitals overlap, we gain some kind of interference, both constructive and destructive, and we generate two molecular orbitals. The same number of atomic orbitals in creates the same number of molecular orbitals out. So the first kind of molecular orbital that's created is a bonding molecular orbital. And this arises from a constructive interference between neighbouring atomic orbitals. The energy of the molecule, therefore, is lowered relative to the two separated atoms if the bonding orbital is occupied by electrons. And that makes sense, because otherwise two atoms wouldn't react to form a bond if their energy wasn't lowered relative to the two atoms in their separate isolated states. And what we see then is a bonding character, and that bond is ascribed to the fact that there is a resulting enhanced amplitude between the two nuclei. Okay, so the energy level of the molecule is lowered relative to the two separate atoms. The electrons in this region have an enhanced probability then of being found in that internuclear region and can interact strongly with both nuclei. So we're developing our theory further now of what is a chemical bond. But of course, when two atomic orbitals overlap, we can also get destructive interference. And we then generate an anti-bonding orbital. And this gives rise to a nodal plane between the two nuclei. And if this molecular orbital is occupied by electrons, then the energy of the molecule is higher than the two separated atoms. So let's have a look at the molecular orbital energy level diagram for hydrogen, molecular hydrogen. So here we've got two hydrogen atoms that come together, their atomic orbitals overlap, and they form two molecular orbitals. And we can draw that as an energy level diagram, and it depicts each of the formed molecular orbitals relative to the two atomic orbitals from which it is constructed. So in hydrogen, the XA and XB there are the hydrogen 1s orbitals that are overlapping to generate a bonding and anti-bonding molecular orbital. And you'll see that the two electrons, one from each of the 1s orbitals of hydrogen, go into that bonding molecular orbital. And their energies are lower relative to the two separate hydrogen atoms. And you'll learn about this in further chemistry study, that we use something here called the Pauli exclusion principle, which essentially limits the number of electrons in a molecular orbital to 2 and tells us that they must be spin paired. So one electron is spin up and one electron is spin down. Now there are possible permutations in this. The left diagram there shows conventional molecular hydrogen with 2 electrons in the lower bonding molecular orbital, But theoretically, we can also get H2+, in which an electron is removed from molecular hydrogen. And because we've removed an electron from the bonding orbital of hydrogen now, we would predict a weaker bond because there is only one electron present in the bonding orbital there. And indeed, this ion does exist, but it only transiently exists in the gas phase, and it's very, very unstable because of that weak bond. We could also have H2-, the diagram on the left there. And the third electron there occupies an antibonding orbital, so it goes into that higher energy level antibonding orbital, and ultimately weakens the bond and destabilizes the molecule. And we can also imagine a situation where we have 4 electrons in the system, 2 electrons in the bonding orbital and 2 electrons in the antibonding orbital. Here we would actually predict no net bond, because essentially the 2 electrons in each of the bonding and antibonding orbitals cancel each other out, and the molecule would not be stable. Okay, so that's an introduction to molecular orbital theory there, and I want to just talk about some slightly more complex systems, but still where we have 2 atoms of the same type in a diatomic molecule. So these are called homonuclear diatomic molecules. A good example of that, or of one that's slightly more complex, is oxygen, where 2 oxygen atoms are going to bond together. But there are more orbitals, there are more atomic orbitals now involved for overlap. And here the basis set consists of 1 valence s orbital and 3 valence p orbitals. What we have then is when the valence orbitals of 2 oxygen atoms overlap, is 8 atomic orbitals that are going to overlap. A 2s atomic orbital from each atom and 3 2p atomic orbitals from each atom. And the atomic orbitals then are described, as we said, as the basis set, and they're shown on either side of the energy level diagram there. And there are 2 types of overlap that we can consider here. The sigma orbitals are formed by overlapping atomic orbitals that have cylindrical symmetry around the internuclear axis. So look at the diagram in the bottom right there. Overlap whereby we have cylindrical symmetry around the internuclear axis are the 2s orbitals and 1 set of 2p, the 2pz orbitals. So these form bonding and antibonding sigma molecular orbitals. And we construct, therefore, 4 sigma molecular orbitals there. And you can see they're labelled 1 sigma G, 1 sigma U, 2 sigma G, and 2 sigma U. There are then 4 remaining 2p orbitals for overlap, with no internuclear symmetry, and these overlap to form pi orbitals. So this is from an overlap between 2px and 2py, or atomic orbitals, and this gives rise to 2 pairs of doubly degenerate energy levels, the 1 pi u and 1 pi g bonding and antibonding orbitals respectively. So what about nitrogen? So another homonuclear diatomic molecule. Well, the principles are exactly the same. we have exactly the same contributing valence orbitals, but if you look very carefully at these diagrams, you'll see that the order of the 2 sigma G and the 1 pi U molecular orbitals is reversed. And the 2 sigma G is higher in energy now than the 1 pi U, and this doesn't happen for oxygen. And you see this as you go across the periodic table. If you were to draw the energy level, the molecular orbital energy level diagrams for these diatomic molecules, that from lithium through to nitrogen, the arrangement is consistent, and then suddenly at oxygen and fluorine, the 1 pi U and that sigma G orbital switch places. And this is entirely due to the increasing separation of the 2s and the 2p orbitals as you move right across period 2. Those orbitals will mix very nicely when their energy levels are very similar, and you can see that's the case from lithium through to nitrogen. So we're talking about the purple and the 1 pi U, the black orbital below it, from lithium through to nitrogen. You see that flips when we get to oxygen and fluorine. For lithium through to nitrogen, those orbitals mix very nicely, and because there's very little difference in their energy levels, each one of those sigma molecular orbitals is a mixture of S and P character. So when they overlap, they're S and P like. But as we move to oxygen and fluorine, the 2s and the 2p atomic orbitals become far more separated, energetically speaking. And those molecular orbitals become either more S in character or more P in character. And that's why you see this flip here. We can define, I'm talking about lithium through to nitrogen now, we can define a highest occupied molecular orbital, a HOMO, and we define this as the molecular orbital that is occupied last. We can also define a lowest unoccupied molecular orbital, or a LUMO, and this is the next higher molecular orbital to the HOMO. So for example, for nitrogen there, the highest occupied molecular orbital is the 2 sigma G, and the lowest unoccupied molecular orbital is the 1 pi G. These are important orbitals, and they're important from a theoretical perspective, but they're also important when we're thinking about predicting structural and kinetic properties. So essentially shape and reactivity of these molecules. They're called the frontier orbitals, and they play a really important role in structural and kinetic studies of molecules. So look here, these coefficients, that's Ca and Cb, which describe essentially how much overlap you get from each atomic orbital, are different. If Ca is greater than Cb, then the molecular orbital is composed principally of Xa, of the character of the orbital is principally that of atom A. And the electron that occupies the molecular orbital is more likely mathematically to be found near atom A than atom B. The same is true if Ca is less than Cb. The electron is more likely to be found, the electron in the molecular orbital is more likely to be found near atom B. And those elements that are more electronegative make the larger contribution to the bonding orbital, and the less electronegative elements make the greater contribution to the anti-bonding orbital. Sigma molecular orbitals. And it leaves then the 2px and 2py orbitals completely unaffected because they have pi symmetry and they don't have a valence hydrogen orbital of that symmetry to overlap with. So these are examples of non-bonding orbitals. And these non-bonding orbitals, mathematically speaking, are confined to a single atom. That 1 sigma bonding orbital then is predominantly fluorine 2s in character. The 2 sigma has both hydrogen 1s and fluorine 2s character, and the 3 sigma is antibonding and principally hydrogen 1s in character. And we can start to see then how electrons fill this system. 2 of the 8 valence electrons enter that 2 sigma orbital. 6 more enter the 1 sigma and 1 pi. And you'll note then that electrons occupy molecular orbitals that are predominantly on the fluorine atom. And the model here would predict that hydrofluoric acid is polar with a partial negative charge on the fluorine atom. And of course, that's exactly what we see experimentally. Now, you can study carbon monoxide. It's a lot more complicated than hydrofluoric acid. Both of these atoms now have 2s and 2p orbitals, and you get a very large number of molecular orbitals produced. We can speak about the HOMO and the LUMO. And I should mention here that N is the number of electrons in bonding orbitals, and N star is the number of electrons in anti-bonding orbitals. There's a little tutorial sheet for you to have a go at on the Moodle page. Have a go at the questions, pause the video here, and I'll go through the answers when you're ready. Now, this question asked you to draw and label a molecular orbital energy level diagram for the gaseous molecule dicarbon, and it then asked you to show the electron configuration for this system. And the astute among you would have looked back in this presentation to when we were talking about homonuclear diatomics, and you know that the arrangement of these orbitals, the molecular orbitals, is exactly the same from lithium through to nitrogen. When you construct that energy level diagram and you start filling this with electrons, remember, you know how many valence electrons are present in the system, so you just fill them up from the bottom with 2 electrons per orbital. You can calculate the bond order, and you know that you've got 6 electrons there in bonding orbitals and 2 electrons in anti-bonding orbitals. So you calculate a bond order of 2. The next question on tutorial sheet 1 asks you to conduct exactly the same exercise, but this case for lithium, and asks you to make some conclusions about the strength of the Li2 bond. Well, of course, here the bond order is only 1, so you would predict that the strength of that bond is lower. Okay, so hopefully what you've gleaned is that we can use molecular orbital theory as a model of bonding in molecules. And it uses this approach of the linear combination of atomic orbitals, essentially atomic orbitals overlapping to generate molecular orbitals. And electrons fill these systems in a very similar way to the way they do in atoms. What I don't want you to worry about is whether or not you have a deep understanding of this topic. I won't be examining this topic, but I thought I would include it because it's a very important model of bonding, and you will get it from other areas on your course. But it's important to introduce it here because I'm slowly increasing the complexity with which we consider how atoms assemble.